So this is a marble that rolled down this ramp and rolled off onto the table. This is shot at 120 frames per second slow motion, and I had tracker look at every third frame. So we're looking at about 40 frames per second here. You can see the parabolic path, and I hope from previous discussion you now know that we deal with this motion, we solve for information about it by really solving two problems. How quickly does the marble move left or right? And since there's no left or right forces, that's a constant velocity linear position time graph. And how does the marble move up and down? And since there is a vertical gravitational force, that gives us a constant acceleration parabolic graph. In this video, we're going to carry out a lab on projectile motion. And you're kind of looking at one way that you can study projectile motion, video analysis, tracker. If you have a large enough object and you have a camera that can record in slow motion, which most cell phones at this point can, you can set the camera up, watch the motion. You can know exactly what time a marble leaves and when it lands. We're going to do a more traditional projectile lab here. We're going to use the time of flight as really the link between horizontal and vertical motion. Typically we would use this little ramp, which has a stop at the end that you can hold the marble against. We would clamp it to the table like this and let it go. And you use the spot where it landed to calculate the velocity of the marble. Since we don't have access to these this year, we'll do it at home. And we'll do the best we can to get a good measurement for the speed of something coming off a flat surface like this tabletop using just equipment I think you'll be able to find around your house. So here's the things you're going to need for this lab. A coin that you can flick off your tabletop, a ruler, and I'm using just a regular ruler here because I'm suspecting most people can get their hands on one. If you have a yardstick or a tape measure that can measure larger distances, that'll be helpful for you. A pencil, some paper, some tape, and then something that's got a weight on the end that you can hang down. I'm guessing most people have earbuds, and we're going to use this to dangle down and figure out what place on the ground is directly below the tabletop we're shooting the coin off of. It's called a plumb bob. Fishing line and a sinker would work awesomely. Really anything that can have enough weight to make the thing hang straight down. And that's just so you know exactly what spot on the floor is right below the edge of the table. Also, you may want to have a phone that you can kind of record the thing hitting the ground. That might help you identify where it hit later. We're going to need basically the height above the ground of our table, and we're going to need to see how far horizontally out a projectile actually goes. So let's look at how we get the height first. Tape down one of your scraps of paper and basically dangle the weight right over the paper. You want to have a little bit of distance so it's easy to mark, but the thing can hang freely. Obviously these earbuds are not perfect. They're not moving in exactly a straight line. It's going to be good enough for this experiment, but if you have something with more mass, it might be better. So anyway, that's directly below the edge of the table. Pinch your finger right where your weight is at the edge of the table and grab whatever you're hanging down at that point. Now we can measure the length of this, and that will be the height of the tabletop. All right, so now all you have to do is flick your coin horizontally off the table. Hopefully your cat doesn't mess with it too much. And now we're going to try to get just the horizontal distance from the X I made over to where my coin went. Notice I'm going to try to ignore vertical displacement. What I mean by that is that the coin didn't just travel straight in this direction. It kind of traveled diagonally. That's going to be something very hard to control. And we would actually be looking at three-dimensional motion rather than two-dimensional motion, were we going to try to actually study that. So what I did is I just kind of went horizontally. I kind of used these floor tile lines as a guide, but I think you can eyeball it. And the distance I'm going to be measuring is from here to here. So we're going to ignore this distance. All right, so 51 centimeters. All right, so there's my final number, 67 as my vertical displacement and 51 as my horizontal. Let's crunch these and figure out how fast that quarter went. Okay, so here's my work for this, and I don't mind if you see it because you're going to have totally different numbers. Key points. Your coin is leaving the tabletop horizontally. That means the horizontal component of the original velocity we don't know, but the vertical component is 0. It's not moving up and down as it leaves the table. I like to set my reference frame with the origin on the ground under the launch point. I think that makes it pretty easy because XO, YO are 0, Y-intercept. X, Y is X-intercept, 0. I think even if you haven't been making a really formal table up till now, there's now so many letters, there's so many variables that just being super organized here is really important. So I strongly recommend making a table like this. Once you've got it all, you're just going to solve 2 copies of an equation. And as we've seen, time is the link because it takes just as long for your coin to travel as far as it does as for it to drop the full height. It does those 2 motions at the same time. In fact, they're really just one motion. So anyway, I solved for a time of 0.37 seconds in the air. I plugged that in. That means my quarter left the table at 1.38 meters per second. So I need you guys to do similar work and figure out how fast your coin left the table. So what we would usually do next is we move the ramp up to a different height. What's interesting about that? Well, because we can always start the marble at the same place, we can guarantee that the marble is going to leave here at the same velocity. So what does changing the height do? Well, it changes the vertical distance. That's going to change how long the marble's in the air for. If the marble's in the air for longer, it's going to have more time to go out. So it's going to land in a new place. So what I ask students to do in a normal year is I say, okay, now you've calculated a speed, how fast it leaves the ramp if you start at the top. I want you to predict where it's going to land. And then I don't let them do anything until they've calculated it. And I make them put an X on the floor where they think it's going to land. Only then do they get to go. As you can see, it's often pretty spot on. So we can't do that this year because we don't have anything like this ramp. Every time I drop the marble from this point, the marble leaves with the same velocity. There's nothing like that with your coin. Every time you flick the coin off the table, it's going to have a different speed, and there's no way to compare the two. But if you know the speed, you can definitely make a prediction where it's going to land. I love this lab. There's something about hitting the mark you make on the floor dead on that really underscores that all this math and this theory and this idea that we break motion into 2 dimensions, that really is how the universe works. It can seem very abstract, but all of a sudden, bam, it hits you right on the nose, basically. So I think that's cool. It also helps you with the conclusion that we write. When we're talking about measurement error, we usually just look at our measurements and say, oh, well, maybe I didn't hold the ruler right, or maybe I didn't press the stopwatch right. But the fact that as long as we have an object that always leaves at the same speed, which we do with these ramps if we started here, it's so precise that we can make predictions and be spot on. The reason this is so much more precise than other measurements we've taken is that we're not using a stopwatch. We get time by measuring the vertical height. And since that's something we could do after the fact, we don't have that having to make a judgment on when to start and stop.